All right. Our next topic is hydrolysis. Hydrolysis, the hydro means water in Greek, lysis means break apart. So we're going to figure out what happens when we throw a salt in the water and it breaks apart. Does it make an acid, base, or a neutral solution? Our goals, the first two are pretty straightforward. We've seen it, we've done these, some of you have done it since grade 11, but exactly the same as what we did in chapter 3 in our solubility. So dissociation equations, net ionic equations, so they're exactly the same. The predict whether salt in this solution will be neutral, acidic, or basic, and basically we just compare the K and B values and find out if it acts as an acid or a base or it's neutral. We also want to determine whether an amphiprotic ion will act as a base or an acid in solution. So again, amphiprotic, we see it on both sides of the table. We want to find out which one wins out. Is it Ka bigger or is it Kb bigger? All right, so let's get into it. Hydrolysis of salt. This is our textbook definition, the reaction between a water and the cation or anion or both of a salt to produce an acidic or basic solution. So remember our spectator ions. These are the conjugates of the strong acids and strong bases. They do not undergo hydrolysis in water, so they're going to just produce a neutral solution. So if we look on your table, I'll talk more about this later, but if you look on your table, the top 5 on the right, so from ClO4 minus down to NO3 minus, those guys are all spectators. Notice there's no arrow going left. H2SO4, also the conjugate of a strong acid, but you're going to see it down on the left as a hydrogen sulfide ion. So it doesn't, it's got different things. So we'll worry about that one later on. That's an amphiprotic ion. But the spectator ions, they do not undergo hydrolysis. All right, so spectator cations positively charged ions. So in general, you can see all the ones on the column 1 of the periodic table. They're alkali metals and our alkaline earth metals in the column 2. So those are all spectator cations. Anions, like I said before, the top 5 strong acid conjugates. So on the Ka table, so again, ClO4 minus down to our NO3 minus. How salt affects the pH of water. So we want to determine the ions produced, ignore spectators, and so the remaining ions are acids if they're found on the left and bases if they're found on the right of our Ka table. So pretty straightforward. If it's on the left and it's only produces an acid, then it's going to be acid solution. If it's a base, then it's going to be a basic solution. All right, so let's look at one active ion. These ones are all the same. So active ion, so this means it's only on the left or the right, right? So for this one here, NH4Cl, we see Cl minus will be a spectator ion, so it's not going to do anything. So our only active ion will be the NH4 plus. So it's found on the left side of the table. So we look at it. All right, so it's all the way down there. This is ammonium ion, and it's got a Ka 5.6 times 10 to negative 10. So then it's going to be act as an acid because it's only producing H3O plus. Acts as an acid because it produces H3O plus. Doesn't produce anything else. All right, so the resulting solution is acidic. All right, a little bit more complicated if it's an amphiprotic ion. So this means we find it on both sides of the table. It can act as an acid or it can act as a base under different conditions. So we want to find out which one wins. Is it the acid, the Ka larger, or the base, the Kb larger? So if it's acting, so base, Kb bigger than Ka, acid, Ka is greater than Kb. All right, so if the predominant hydrolysis is acid hydrolysis, acts as an acid. Base hydrolysis acts as a base. So we just want to find out which one's winning in this one. So let's look at this NaHC2O4. So our HC2O4, this is our hydrogen oxalate ion. All right, so find that guy on your table. Find it on the left side first. All right, so do the Kas. They're always the easiest. So we find it on the left. It is at 6.4 times 10 to negative 5. Exact number by the table. Write it down. 6.4 times 10 to negative 5. That's our Ka. Now we got to look at the Kb. Kb is a little bit different. So we want to find it on the right. So we're looking for our HC2O4 minus on the right side. And so that's going to be down at 5.9 times 10 to the negative 2. All right, so you see it there. So it's the oxalic acid. It's a conjugate of that one. All right, so C on the other side, 5.9 times 10 to the negative 2. So we're going to find the Kb by doing the Kw divided by our Ka of the conjugate. All right, so a lot of students wanted to do the Ka of the 6.4 times 10 to the negative 5. Don't do that one. All right, you're going to get the wrong answer. So we see that our Kb is going to be 1.7 times 10 to the negative 13. All right, once we do the equation. So very easy, Ka greater than Kb. So therefore, it's going to act as an acid. Right, that over. So it's going to act as an acid. All right. Next one. All right, so now we're going to have both ions active. So we got NH4, NO2. We throw them in the water. Water breaks them apart. It's going to be NH4 plus and our NO2 minus. All right, so NH4 plus, just like before, it's going to be producing H3O plus. NO2 is going to only go the reverse way when mixed with water, and it's going to be producing OH minus. All right, so we want to find out which one we get more of. Do we get more H3O plus or more OH minus? So the Ka of NH4, and the Kb of NO2. So our Ka, right from the table, NH4, look at it. All right, there it is, 5.6 times 10 to the negative 10 from the table. Kas are easy. Kb, so the conjugate of our Kb, so Kw over the Ka, the Ka of HNO2. Look for HNO2 on your table. There it is, 4.6 times 10 to the negative 4. All right, so Kw divided by your Ka, and that will give us 2.2 times 10 to the negative 11. Compare the values, right? Negative 10 is greater than negative 11. So therefore, Ka is greater than Kb, and the solution will be acidic. All right, no problems. Keep going. So talking about cations which hydrolyze. So hydrated cations, these are metals from the center of the periodic table, which are smaller ions, and they have a larger charge. If you remember back to chemistry 11, as you go across a periodic table, you're building nuclear charge. So this is going to attract water molecules. So they have, so for this one here, we got Fe3 plus, mix Fe3 plus, and it's going to make this FeH2 3 plus. So find this on your table. This is hexa aqua iron. All right, try saying that 3 times fast. You can also call it iron 3 ion. And it will act as a weak acid in solution. So this is the equilibrium it's going to produce. And you can just get that right from your table. 3 common hydrated cations. We got Fe3 plus, Cr3 plus, and Al3 plus. Find them all on your table. Star them. This is Fe3 plus, Cr3 plus, and Al3 plus. Fe is 6.0 times 10 to the negative 3. For Ka, Cr is 1.5 times 10 to the negative 4, and Al is 1.4 times 10 to the negative 5. All right, notice these guys, they're going to try to trick you with them all the time. These guys will form weak acids. All right, don't say they're neutral solutions in your tests or quizzes. They're going to form weak acids. All right, so what happens to the pH of a solution when AlCl3 is added? So AlCl3, we can think of this as AlH2O6 and then Cl3 plus. The Cl is a spectator. It's going to go away. It's going to make the hexa aqua aluminum ion or aluminium ion, depending on how you want to say it. So this is the equilibrium that it's going to form. All right. So AlCl3, that's the same as doing our aluminum ion. All right. So just note that you're going to lose those spectators and you're going to get that weak acid when it mixes with water. All right, so it's going to increase the H plus concentration because we're producing H3O plus. All right, so weak acid. pH will decrease. Okay, next, acidic and basic anhydrides. Anhydride is an oxide compound that reacts as an acid or base in solution. So we have acidic anhydrides. These are non-metal oxides. So some common non-metal oxides, NO2, N2O5, SO2, SO3, CO2, Cl2O. So all of these react with water to form acids. So there's a bunch of different mechanisms that's going to that will come into play with this. We don't have to know these mechanisms. We just have to know that non-metal oxides, you throw them in water, they're going to form acidic solutions. This will come back a little bit when we're talking about acid rain further on in our chapter. All right, so again, they ionize in water, right? You notice they're all producing H3O plus in the solution. All right, the other pair for this one, these are basic anhydrides. So these are metal oxides, common metal oxides, right? Na2O, CaO, MgO, CaO, right? I put CaO twice. I guess it's pretty important. So these are ones that they have spectator cations and oxygen. So these react with water to form bases. So here's a mechanism. So that spectator, that Na plus is going to go away. You're going to have O2 minus. Again, BaO, you're getting the O2 minus. These O2 minus react with water, and then you're going to form hydroxide. That O2 minus, very, very electronegative. It's going to pull those H's right off of the water to form the hydroxide ion. All right, so both steps written together. So you're going to get NaOH, and then the active will be the OH minus. All right, so to recap, metal oxides form basic anhydrides, non-metal oxides form acidic anhydrides. That's all we have to know. We throw these metallic oxides in water, we get a basic solution. We throw these non-metallic oxides in water, we get acidic solutions. All right, so no mechanisms. We don't have to know anything about it. We just have, this is the only thing we have to know, right? Metal oxides, basic, non-metal, acidic. All right. Good questions from your book, page 148, 69 to 73. Put questions in the chat if you have them. All right.